Welcome guys in this video session. So in this video we will discuss about the adaptive equalizer, how to train the adaptive equalizer. And in the previous video we had discussed the detailed overview of the equalizer. So guys, before starting the video I want to tell you, please subscribe my channel if you have not subscribed yet, and then like the videos. So if you have any query regarding any video, then please write in the comment section. So let's start the video. So what is equalizer? What are the adaptive equalizers? Basically, adaptive equalizers are the equalizers basically that have used the adaptive algorithms and have used some weights, and these weights are changed accordingly the output and according to the error signal. So these weights are changed in this basically adaptive equalizer. So there the adaptive algorithms are used and weight system are used in this adaptive equalizer. So all these things we will discuss later in detail in this video. So here firstly basically this is a diagram, figure equalizer using training sequences. So here in this diagram, here y of k is the input signal that is in the receiver, the output in the basically in the receiver the input signal that goes to the equalizer basically in the receiver. So y of k is the input signal that goes to the equalizer. These z inverse, these are the blocks basically, or we can say these are the delays blocks, and y of k basically k is the vector. So k may be 1 to n number of the k's are there, the value of k. So here y of k is the input signal, and for y of k signal basically this weight w of k weight, wk weight is used here, and after basically this z inverse is a block where give the clock retraining signal for the every delayed input signal basically. So y of k minus 1, this is the another delayed signal or another delayed input signal. So this signal is clocked by this, and then again y of k minus 2, this is the also another input vector signal basically for equalizer, and with the help of this block this is clocked and retrained. So for up to k minus n blocks, here this is the k minus n input, so this will be retrained and clocked with the help of this block, sample block. So these are the weights w of k minus 1, w of k minus 2 up to w of k minus n, kn. So these weights are may be changed accordingly. So here basically these the input signal, and here this is the expected value or the summation of this all these weights. So here this is the output, estimated output of the equalizer. So here this is the expected value for or summation or subtracting values for the error signal. Here if any case there is an error in the output so this error, this signal will be feedback to this adaptive algorithm, and this is the e of k is represent the error signal, and according to the this adaptive algorithm and this error signal, so each weight may be changed continuously, and basically here these weights, this signal will be multiplied this for all the weights, and when if in case of any error in all these inputs up to number of the delays y of k minus 1, k minus 2 up to k minus n, all these signals. So for all the signals with the help of adaptive algorithm, so this signal will be individually multiplied with these weights. So basically here this weight, these are the multipliers. So this signal will be multiplied with weights, and according to this error signal, each time for each input vector the weights will be updated continuously. So we get the at the output the updation state of this weights. So with the help of these weights we get the output or desired output at the equalizer. So with the help of these weights our received signal reaches near to the optimum value of this signal basically. So this is the basic overview of this figure, this diagram. Here this is the d of k is set to x of k. What is x of k? X of k is basically the input signal that is received at the receiver basically, and y of k is the input signal for equalizer that is used in the receiver. So basically we want at the output x of k that we have transmitted. If you have not watched my previous video, then please watch that previous video, and these all things are discussed on this previous video. So if you watch that previous video, then you will easily understand this video. So please watch that video. So here this xk is the input signal, and we want at the output or dk is the actual output. We want this x of k or original signal that is transmitted from the transmitter, and we want at the receiver this signal basically. And dk is set to x of k or represent a known property of the transmitted signal. This represents the known property of transmitted signal. So here equalizer is a time varying filter basically, so which must constantly retuned. So retraining sequences may be used here. So equalizer is varying with time, filter is working like a filter. Here this k subscript that is used here that denotes the discrete time index values, and y of k that I have already discussed. Y of k is the input that is used or that give to the equalizer, and this y of k signal is basically a random signal that is received basically firstly at the receiver. The signal that is received y of k, it have lot of noise and random values of the signal. So desired signal that is transmitted from transmitter to the channel, and after receiving the channel there is a random signal, so that is this y of k. So input y of k that is signal that is the input to the equalizer, that is a random process signal that give to the equalizer input. So here the n number of the delays are there basically. These are the n number of the delays, and n plus 1 taps, these are the n plus 1 taps, and tunable multipliers are there basically. Tunable multipliers are the weights basically. These weights are the tunable multiplier. These are working like a multiplier basically. Any type of error signal that is multiplied with these weights, and according to this error signal and adaptive algorithm, each weight is updated and get the output at the equalizer basically. This at the estimated output at the equalizer. So here the difference between the k and new value of k, or we can say this only k and this delays value of k, is these values are varying with time. So only there is a difference of time, and z inverse, these are the blocks where the number of the samples has been clocked to the equalizer and retrained to the these different vectors. So here if we want to find out the new weights, how we can find out the new weights basically. Here new weights equal to previous weight. If you want to find the new weight, then you have to know the value of the previous weight plus constant value that is multiplied with previous error and also multiplied with the current input vector. All these values we need to find out the new weight equation basically. These things we will discuss later. So here if you want to find out this previous weight, that is equal to previous desired output is subtracted with previous actual output. So basically desired output is subtracted with actual output, so we find out the error, basically previous error. So here basically this constant, this constant may be adjusted by algorithm, this adaptive algorithm, to control the variation between the weights. Basically only constant behaves like a controller to control the variation between the weights, and their process is repeated continuously in loop while equalizer attempts the converge. So while the output d of k is equal to x of k, then this equalizer or these weights continuously updating. If we get at the output the desired signal, then these weights or freezes or stops for updation, basically. Then here this process is repeatedly continuing and in loop while equalizer attempts to converge. Converge means here when at the equalizer we get the desired output. So then the equalizer freezes the weights until the error exceeds the acceptable level or new training sequence is sent. If the error signal is exceeded their acceptable level or any new training sequence is sent to the equalizer, then again the weights are starting to updation, and again this error process is started, and so on. So if we minimize the mean square error, basically this is behaves like a cost function. So mean square error, then bit error rate may be reduced. So basically what we are doing here in the equalizer, so equalizer basically helps to minimize the ISI, inter-symbol interference, and that causes the bit error rate there. So in the previous video I have discussed all these things. So basically we want to minimize the mean square error in this equalizer, and due to that the bit error rate automatically be reduced. So here the mean square error, how we can find that? For we subtract the signal, or we subtract the desired output. Here this is basically here this is the d of k, basically here this is the d of k. So this cap denotes the estimated output of equalizer, and only d of k is the desired output of the equalizer. So if we subtract both desired and estimated output, then we easily find out the value of mean square error. So here the mean square error is denoted by expected value of this error signal. Basically this we need to find out the expected value or all the equations of error signal, that is e of k, and multiplied with conjugate of the e of k. So this is the denotion of this mean square error. So we denote the MSE, mean square error, is expected value of the error signal dot conjugate of this error signal, basically. And a known training sequence must be periodically transmitted, and here the unknown training sequence or we can say pilot signal sequence must be periodically transmitted when a replica or transmitted signal is required at the output of this equalizer. So what is the replica of transmitted signal? Or it is the same copies of this transmitted signal. So when these signal will be required at the output, so this periodically transmit the training sequence or pilot sequence may be periodically transmitted to the equalizer. Here next, due to the training sequences, the adaptive algorithm receiver able to compute and minimize the mean square error. Basically here this is the due to the adaptive algorithm that is used in the receiver. Due to that the training sequences, this will be able to compute the due to the training sequences, the adaptive algorithm will be able to compute and minimize the mean square error. So for the adaptive equalizers, here this will use the here in the derivations of this adaptive equalizer, here this is use the matrix algebra. Basically some matrix are used there. So here we will discuss the equations one by one. Here basically this y of k is the input vector or input signal that is give to the equalizer, basically that we have seen in this figure here. So here, yes, here this y of k, basically here this y of k is the basically input signal, and this is the basically input vector. Here the k have the different values, and this is the input signal for different signal, and the signal that are reaching at the inputs or at the receiver at a different time instant. These are the y k minus 1, k minus 2. These are the same signal, or these are receiving at the receiver with different time delays, basically. So these are the input vector signal, and w of k is also the weight signal vector for k number of the delays. So these things we need to remember in the derivations. So let's move to below here. Sorry, it's taking time. So here y of k is the input, basically input vector. Y of k is the input vector, and here the input vector, the value of this is input vector, that is y of k minus 1 up to k minus n. Basically this is a input transpose vector, or in the simply a raw vector of y of k up to k minus n values, basically. So here this is the input signal, basically input signal, and this d of k, this cap represents this estimated output of the equalizer. That is how we can find this. Basically here take the expected value, or take this summation of this. Here this is summation, where the values of this small n from 0 to capital N, and w of n k, w represents the weights of n values. N have also values from 0 to capital N, and maybe scalar, basically, and k is also k represents the input time delays, and y of k minus up to y of k minus n. Basically these values are maybe you take the summation of these all these values, and in the equation second, and this is for the output of the equalizer, basically estimated output. This is the estimated output of this equalizer. Now for equation third, this is the equation for the weights of this equalizer. So or we can say multiplier of this equalizer. So here w of k, here is also, this is also a raw vector here. So w0 of k or w naught of k, basically for this y of k, and this y of k for this y of k minus 1 for w of 1k, y of k minus 2 for w 2k, and up to y of k minus n for w n of k transpose. Basically the size of these vector may be same. So here this is the basically w of k, w naught of k to w of n of k up to these values. So this is a raw vector for weight equation, or multiply vector values. So if we substitute this equation first, second and third, then this estimated output, the output of this equation, this equalizer equation, that will be equal to, that is y of k, after this y of k transpose dot w of k. The output, basically this input vector is multiplied with weights, and that will be equal to basically if we transpose the elements of this input vector y of k, and that is multiplied with this simply weight vector, or we can change this, we take the transpose of this weight vectors here and multiply it with simple y of k column vectors. So here the rows vector or rows and column multiplication here, and we get this desired, basically here we get the matrix values, desired output, or basically, or we can say this estimated output of this equalizer here. So here E of k, that is the error signal, and how we can find out the error signal, basically we subtract this desired output minus estimated output. So we get here we are subtracting the desired output with estimated output of the equalizer, and we get this equation, basically this equation x of k is the transmitted signal that is transmitted from the transmitter. This is important point to remember. X of k is the basically input signal that is transmitted from transmitter, that is, and minus y of k transpose and multiplied with w of k, this equation, this above estimated equation, and subtracted with this equation, basically x of k minus w of k, or we can subtract with input or desired output in the basically in the desired output what we want x of k that we have transmitted from the transmitter. So that is why we have taken here x of k is represent the desired output minus this estimated output. So we get the error signal, and we need to compute the mean square error of this error signal. So here take the mean square values, here absolute values there. So here the value of the E of k, that is x of k, that is x of k minus this equation y of k transpose dot w of k, or we can also take this value. So here this is the formula here, that is a, if we a square plus b square, that is here, if we, or we can say here, basically here the value of E of k, that is x of k minus w of k transpose into y of k, basically. So if we take the square of this, then here this is also the square of this. So here this will be the, what is the a minus b whole square. So it will be basically this is the a square plus b square, basically a and b, this is a square plus b square minus 2ab. So this formula is utilized here in this equation. So here this formula is utilized in this equation here. So here the error signal, that is this is the a square plus b square is the this w of k, this value w of k transpose y of k, again w of k transpose y of k minus 2 times ab, 2 times a is the x of k dot y of k transpose w of k. This equation is equation 6. So taking the expected value, or find out the calculations of these values, and take the expected value of this error, and then expected value of this xk, this all this value, take the expectation of this, and w of k are the constants are there, that will be outside these brackets, and take the only the expected value of these vectors, basically input vector, and that this y of k and y of k transpose, and then find out this how next in the next slide. Move to the next slide. Here we find out the cross correlation of these vectors, cross correlation values of this vector or input vector, basically. So here this is the expected value of this desired output x of k, or the transmitted signal that is transmitted from the transmitter x of k, plus these are the weights, and expected value of the y of k, the input vector, input for the equalizer. This y of k is the input for the equalizer, and x of k is the input signal that is transmitted from the transmitter, and w of k are the weight vectors, basically, and this is minus 2 times expected value of this x of k, y of k transport. This is the input signal that is transmitted from the transmitter. Y of k is the input for the basically equalizer, and w of k is the weight. So let's move to the next slide here. So now we need to find out the cross correlating values of the vector of basically input vector. So to know about the input vector is correlating with the output of equalizer or not. So here we want at the desired output, basically this is the estimated output, that is equal to x of k. So we want the x of k at the output of the signal, that x of k is the signal that is transmitted from the transmitter. So here we consider the p as the variable, that is equal to the considering the p as a correlating vector p. So here taking the correlating, basically consider the correlating vector p, the value of p that is equal to the expected value of this input for both the input, the x of k, or basically x of k we can say that is a desired output that we want at the output, and y of k is the input vector that is that the input that we have give to the equalizer. So expected value of these both, that is equal to the expected value. So x of k time y of k, x of k is multiplied with the different values of the y of k that is received at the equalizer. So x of k is the basically a simple common thing that we want at the output. So y of k is the input vector that we are receiving as an input to the equalizer. So we receive the k minus n values. So here x of k is that we want, and y of k minus 1, y of k minus 2 to y of k minus n. These all these values we will receive at the receiver or at the equalizer equation matrix basically. So here this is an input correlating matrix, or we can say the covariance matrix. With the help of this matrix we find out the basically main signal that we are, the main receiving signal basically that we want to receive. So here r is the variable that we are considering as a covariance matrix. Here covariance matrix here. So how we can find out the covariance matrix? Covariance matrix is found out with the help of this correlating matrix. This are input vector y of k, so we take the n plus 1 n plus 1. So we need to if we want to find out the input correlation matrix, then we need to find out, we use the n plus 1 basically square matrix. So r is the n plus 1 square matrix. Here in the square matrix what we do only this simple, basically all these of the same vector, same input vector is multiplied with their own parts. Basically firstly here in this in the first row, total number of we have total number of these elements we have considered y of basically y of k minus 1, y of k minus 2 up to y of k minus n. If we want to understand in general 1 2 3 and 4, total number of the 4 components we have here considered. Basically here the lot of components y of k to k minus n, but for understanding here we have only considered the this 1 2 3 and 4 components. So if you want to find out this the correlation or covariance matrix of this, then basically this is the we can't take this correlating vector here. We consider this previous equation basically for find out the correlation matrix or covariance matrix. So here this y of k, we consider this we consider this equation y of k equation or input vector for find out this R matrix or covariance matrix we can say. So let's move to this, it's taking time. Yes, so here R is the covariance matrix. So here this only firstly in the first row we have considered this only simply y of k. Y of k is the first element, this first element. So this first element is multiplied with all these delays of same vector, same y of k vector is multiplied with in a matrix form basically. So y of k, we use n plus 1 matrix here. So y of k is multiplied with y of k is multiplied with y of k minus 1 here, y of k again is multiplied with y of k minus 2 up to so on, y of k is multiplied with y of k minus n. No, in the next row here, the after y of k, that is y of k minus 1, second one, this one is taken here, this one is shifted here, y of k minus 1 is multiplied with the whole input matrix y of k, then y of k minus 1 again multiplied with the k minus 1, this y of k minus 1, then y of k minus 1 is multiplied with y of k minus 2 up to y of k minus 1 is multiplied with the k minus n. Basically this here one by one is multiplied with the whole y of k input vector. So here y of k minus 2 is multiplied with again y of k minus 2 is multiplied, or we can say y of k minus 1, k minus 2, all are multiplied with the y of k. Simply one thing I want to I will here write here to better understand you. Basically y of k is equal to y of k minus 1, y of k minus 2 up to y of k minus n. Basically this is a input vector, input vector. Okay, so this input vector is multiplied with this own component. So y, if basically if we this first if we consider this first component and multiplied with this whole y of k in the first row, then consider this second and multiplied with this whole y of k, then consider y of k minus 2 multiplied with this whole equation y of k, then consider y of k minus n and multiplied with the whole y of k. This procedure is continuous up to k minus n. So in this matrix this procedure is considered to this procedure is considered for creating a covariance matrix here. So I think you will understand this, you will get this point. So this y of k minus 2 is multiplied with the whole y of k vector, and then y of up to so on y of k minus n is multiplied with this whole y of k vector basically of all these delayed components, and then this matrix will be created. So this is the covariance matrix, and in the diagonal part, basically in this diagonal part, basically in this diagonal part that have a value of this the information of the main signal, transmitted signal. Basically in the diagonal part, this is the correlating part, or we can say in this matrix have a information of this input signal that is transmitted from the transmitter basically, and all other components that are that we don't want, we only want this identity of this identity form matrix, or this only diagonal component of this covariance matrix. And here R and P, basically R is the covariance matrix, P is the cross correlation vector basically. And if the R and P are the stationary, means if these delay time are fixed and that are not varying with time, then mean square error zeta, that is equal to the expected value of this x k square basically, plus x k square is the basically x k is a transmitted signal, the input signal that we want, and the desired output signal basically, plus these are a weight transpose are multiplied with element wise or covariance matrix with weights minus 2 times p is the cross correlation. Basically what we want, P is the cross correlation vector and W is the weights basically. So here the P transpose and weights, this equation is basically for find out the mean square error or zeta. So this is the training part of this equalizer. Here if we minimize this MSC equation or equation 9 in terms of weight vector W of k, then it become possible to adaptively tune the equalizer to provide a flat spectral response, or we can say the minimize the minimal intersymbol interference in the received signal. So this is due to the fact that when the input signal y of k and desired response or estimated response d cap of k equal to x of k are stationary, and the mean square error is quadratic on weights W of k vector, and minimize the mean square error. If we minimize the mean square error, that leads to optimal solution of the weights, or optimal solution for weights basically. So we want the output of the equalizer have minimizing of this mean square error. So that's all for this video, guys. If you really something get from these videos, then please subscribe my channel, like the videos. So thank you guys.